Hi class. So here's our first video. Our lecture for today is on chapter 4.4, Undetermined Coefficients, the Superposition approach. So there's two approaches to solving by undetermined coefficients. This is the first one. On Friday, I will post a video regarding the second method. I'll probably post it earlier than that, but that's the topic of discussion for Friday. Okay. Now, when we're doing these kinds of equations, we are assuming that the coefficients are constant. Just like in section 4.3, we're going to turn it into a polynomial, right? An algebraic equation that we're trying to factor in order to find the roots for it. Now, for the second half of our equation, where this approach comes in, is that we are solving non-homogeneous equations in this section. Okay, so we're going to combine the two methods. We're going to solve the homogeneous equation by turning it into an algebra problem and factoring, and then we're going to apply these methods by looking at the form of the non-homogeneous portion of the equation and use that to try to figure out what our particular solution looks like. Okay, so just to recap, for the non-homogeneous dE that has constant coefficients, that looks like this. So again, yn is the degree, is the order of our equation. All of these coefficients are constant, okay? And it's non-homogeneous. So in order to try to figure out what our particular solution looks like, we're going to look at what our function we are equal to that's making us non-homogeneous. What does this look like? That is going to tell us the form of our particular solution. So from your book, we had a sort of a guide, okay? And you shouldn't memorize the guide, but you should memorize how it works, okay? So the way g of x looks is the way that our particular solution is going to be performed, right? So let's talk about this a little bit, okay? If we have a constant value, our form of our solution, particular solution, should be a constant. If we have a polynomial, right, so 2, 3, 4 here are polynomials, we will have a general form polynomial of the same degree, right? So notice here, I'm missing a second term. There's no x squared term. My solution could have an x squared term, okay? So the general form of whatever degree the polynomial is what the particular solution may look like, okay? If I have a sine or a cosine, I'm going to have a sine and cosine portion of a solution, because we know sines and cosines are related to each other, okay? So you're never going to have one without the possibility of having the other. So if you have a sine or a cosine, then you're going to potentially have its pair in your particular solution, okay? Now if we come down to 7, if we have some sort of an exponential, I'm going to have a constant multiple of that same exponential should show up, because we know that these show up as solutions to our DEs very, very often, right? So if I have 1, it'll show up in this form. If it can be factored out and have a polynomial factor, then we do the same thing that we did up here with the polynomials. Whatever the degree of the polynomial is, that will be attached as a factor to this exponential, right? So here we have x squared. So here we have the full general form of a quadratic attached to my exponential, okay? Because just because there's no x term or constant term showing up here as a factor does not mean that my general solution, my particular solution will not. Okay, so we write the whole thing as my potential form. And any combination of these. Okay, so that's really what's going on down here, is that we have combinations of these things. The combinations of those things show up in the same form. An exponential with the sine or cosine means I'll have that exponential with sine. I'll also have that exponential with cosine. Okay, exponential with the sine, same exponential with the cosine, right? Because the sines and cosines come in pairs. Here I have a polynomial mixed with my sine. So the general form of that polynomial mixed with cosine and sine, because sine comes in pairs, right? Same thing here. Polynomial, exponential, and sine. So I'm going to have the general form of this polynomial times this exponential times cosine, and I'll also have the same thing times sine, right? So that's the way that it works. So if I see forms like this, I'm putting the combination of the polynomial form, the exponential form, and the sine cosine pair all together. Okay, so it's really about remembering those three things, right? So the polynomial, you're putting the general form of the polynomial, your sines and cosines come in pairs, and if you have an exponential attached, that stays attached through all the terms also, right? So again, that's that superposition approach, where we're taking all of the linear independent sort of functions and we're kind of combining them together, right? Okay, so as you noticed, we have more than one sort of solution for our guess for the particular solution. For this one example, okay, this one has two parts. One part, two parts, right? So my full guess for the particular solution has a part 1 and a part 2, right? So it's a superposition of two different particular possible solutions, right? So if one of our particular guesses, right, for my particular solution is already present in the general solution. So what does that mean? So that means that when this is equal to 0, if we have, let's say, the ax plus b shows up when I do this, and it also shows up here, we have to multiply to get rid of our multiplicity, right? So what that means is we're going to multiply that particular portion of my guess for the particular solution by x to the n, okay? N is the smallest value that's going to get rid of the multiplicity, right? So again, remember, I want everything to be linearly independent. I should not see the same thing pop up over and over again as a linear combination, meaning if I'm adding it over here in the general solution, it should not be added again in the particular solution. So we talked about that in class a little bit, about why does my particular solution look like this if part of this is already in the general solution. I'm not going to repeat it, right? So I need to sort of bump up its power so that it looks different, so that it is not repeated, basically. Okay, so we'll talk about that because the example I do in here, I definitely go through that process. Okay, so I need to make every single guess in my particular solution independent, and all of the forms of my solution in my general solution also have to be independent. Okay, so everything has to be independent. It has to form a fundamental set of solutions, meaning they have to be linearly independent, right? So if I threw them all in the Wronskian, I should not get out 0, right? That's basically what we're saying here. Okay, so let's start with an example, right? Let's go through these steps. So first, I need to solve for the homogeneous equation, which we did in the last section, the homework you just turned in. We're going to do that method. We're going to take all the prime forms, we're going to turn it into an algebra equation, and we're going to solve for that. I have to do that first. Okay. Next, I'm going to look at what that g of x function looks like, and I'm going to base my particular solution on that form. I also have to take into account what my general solution looks like for the homogeneous equation, because if I have basically portions of the solution here that are repeated in my guess for yp, I have to do this thing where I multiply by x to the n to get rid of the multiplicity. Okay, and again, we're doing that for each piece, right? Each linear combination portion. All right. Next thing I got to do is I'm going to take this form that I have for my guess for the particular solution, and I need to differentiate it. Okay, if I have y double prime and some primes, I got to find all those pieces, and I'm going to substitute it back into my DE. After that, I'm going to simplify it, and I'm going to solve for my coefficients by setting the terms on one side of the equal sign equal to the other, right? Equal to this g of x that I have here, and making a system of equations for me to solve. Right, so now we can start with an example. So let's take y to the fourth order minus y double prime equals this polynomial g of x over here. So I'm going to take a little pause real quick, and I want you to guess, right? Write down, hopefully you are taking notes as we're going through this video, right? Don't just watch this video without taking notes. But I want you to write down your guess for the particular solution based on this g of x. So without taking this into consideration right now, just do this part. What do we think that our yp should look like based on this? So I'll give you a second. Okay, so notice here I have two things being added, so I basically have two different solutions I'm looking at. I have one here which looks like a polynomial of degree 1, so I should have an ax plus b, and then here I have a polynomial term being factored in with an exponential. So not only should I have ax plus b from this one, but I should also have another ax plus b times e to the negative x, right? So that's what the general form of this is. Of course, there's not two a's here, ax plus, let's say, ax plus b for this one, and then cx plus d times this one, okay? And then, of course, I need to solve this as well, right? So this is, as an auxiliary equation, m to the fourth power minus m squared, right? So just think about this before you get started, right? Especially this, you kind of want to look at it and assess what you think your solutions are going to be, okay? So let's get started. My auxiliary equation, right? Solving this side first is m to the fourth minus m squared. I can pull out an m squared term, right? And now I have a difference of squares, so I can factor this even further to m squared, m plus 1, m minus 1, which gives me my roots of m0, m1, m minus 1. Okay, so I have a double root here, 0, 0. So my general solution will have this form, right? 1, 0 gives me the constant. The next 0 means I multiply it by another x, because that keeps them from being linearly dependent. It keeps it linearly independent, right? They're not multiples of each other now. I got a 1, so I have c3 e to the x, and I have a negative 1, which is c4 e to the negative x. So this is my general solution, right? This is the solution to the homogeneous equation. Now, I've heard you guys ask a lot of times, how do you know the order? It doesn't really matter the order, okay? These two are paired together because of the multiplicity here. These ones I could have written in any order, it doesn't matter, but we generally would like to write the constants and the multiples of x, the polynomial forms first, and then the exponential forms generally come last, and then the sines and cosines, if they appear, are after that, okay? So for this one, this is the proper order, although these two can be switched. This could have been c3 e negative x, c4 e to the x, and that would have been fine, okay? But we generally keep it kind of progressing into a more difficult form, where the beginning is easy and the end is like the more complex forms of the solution, okay? So from g of x, we can tell that we have two parts. I have one part plus another part. So I'm going to have a particular solution 1 and a particular solution 2. Add those together in a superposition method, and I will have y of p. And my full solution will be y of g plus this whole y of p function. Okay, so we're going to be combining lots of functions together here. So my y of p should look like this. Okay, so remember the book uses a's and b's. We're already using these coefficients, so we'll just continue it going from here. So here I have the polynomial form ax plus b, but of course it's c5 and c6. Then this is another ax plus b times the factor e to the negative x. And of course I'm using C7 and C8 to keep the progression of the coefficients going. Okay. So if I now want to substitute this into my equation, I gotta go, that's right you guys, to the fourth order, right, to the fourth power. I have to take the fourth differential here, right? So I'm gonna differentiate this thing quite a few times. So note that Cix is in both yg and p1. Okay, so what do I mean by that? Ci to the x. So there is a coefficient of unmentioned number, because it happens more than once, being multiplied times x. So C5, right, is in my yp, so C5 times x. And in my general solution, I also have C2 times x. So I have two things that are the same. Also, C1 and C6, those are also the same. Okay, so I need to multiply yp1 by something so that it's not identical to this. And you're like, well, it's not identical. They got different coefficients. But I could add these together. If I add C1 and C6 together, it's one constant. C2x plus C5x, that's one multiple of x, right? So I need to bump this one up in order so that it's no longer equal to this. Okay, so if I multiply this by x, I get x squared plus x, but I still have a constant multiple of x here, so that's not enough. So I have to multiply this by x squared. Okay, if I multiply this by x squared, I get c6x squared, c5x cubed. There is no x squares or x cubes here. So in order for me to get rid of the multiplicity in yp1, I have to multiply this by x squared. That's the lowest value that's going to get rid of the multiplicity. Okay. Okay, so let's look at this next one and let's see if we have multiplicity here. And it seems like we do, because if you notice, I have a C4e to the negative x, and if I were to multiply this out, I would have a constant multiple of e to the negative x. So this e to the x portion doesn't have any multiplicity, but this does. So I'm going to look at this one separately from this one and say, what would I need to multiply this by in order to get rid of this multiplicity? Okay, so since I have one part that's the same, the lowest value of a power of x would be just x. If I multiply this by x, I'm going to get c7x squared plus c8x e to the negative x, and there is no constants times x times e to negative x is here. Okay, so in this example, and this is not common, that's why I chose this one, but here we have two separate things where we have to get rid of the multiplicity. Okay, so as you see here, we must multiply the second form of my particular solution by x to eliminate the duplication, since ci e to the negative x, so some index of our coefficients, shows up in both yg and yp2 as well, right? So here and here. So from yg and yp, I have a constant times e to the negative x. So I got to get rid of that. Okay. So now we can talk about what the particular solution looks like. It looks like this, right? So that first part multiplied by x squared, so it looks different from this now. And this being multiplied by x, so that it looks different from this. Okay, so we got to get rid of the things that look the same, and we do that by bumping them up by powers of x. Okay, so now I can start to take my derivatives, right? So I have my function y prime, so this comes down, this one comes down, and this one we do the product rule, right? So I differentiate the inside, and then I differentiate the outside. So that's why we have the negative here times my regular form. We're going to do this again. Okay. I simplify as I go, but I don't expand everything. So I'm not expanding everything and combining like terms. You can. There's not a problem with that. But sometimes it just makes it more messy, because if I do multiply all these out, right, I'll have this times this, which on the next differential derivative is going to give me another product rule, and then I'm going to do product rule here and here if I multiply this in. So instead of doing product rule, for instance, if I had multiplied this in, I would have done the product rule twice instead of just once, right? So it's really up to you. It's algebra at this point. Well, I guess it's calculus. Do whatever you feel is best for you, right? But for this example, and generally if we do end up coming back to class, I will generally keep it like this when I do this, right? So let's do the next derivative. Okay, so the 2 and the 3 gives us the 6. This gives us just a constant. Here, using the product rule, the constant part goes away here, and this drops down in power. So you have 2c7 times e to the x, and then the second part of the product rule, and then here the product rule gives us these two terms. Okay. Now there's a lot of math involved here, and I know I told you guys to write as you watch this video, so I'll go a little bit slow here so you have time to catch up on the writing. Okay. So again, this is the inside part was differentiated, okay, and the outside stays the same. And here the two negatives come out, so you get positive. This inside is the same, but this outside stays the same here. I'm sorry, it's been differentiated. That's why this is a plus. Okay. I do this one more time. Again, I got to go to the fourth derivative, so I can clean this up a little bit here, right? Because if you notice, I have two of the same things. These two terms are the same, so I have two of them, which lets me clean it up a little bit. All right. So if we do the third derivative, we get this term, right? It's a constant now. This constant term went away. This stays the same, but it turns negative. This gives us the same result we had last time, right? So I'll differentiate the inside part. This constant goes away. This term goes away. So I got negative 2c7e to negative x. And then for this part, I'm differentiating the outside function. So it turns into a positive, and the inside stays the same. And then same thing, these last two terms are the product rule from these terms. So you differentiate the inside to get this times e to the negative x, and then this part is the same here, and this outside part gets differentiated, so that's why we get back to the negative, and I have this term. And if you notice, I have two of the same terms again. Okay, so I can combine these like terms. I also have like terms here. So again, remember when you add like terms, the coefficients have to be the same, right? I can add these two terms now because they're both c7 e to the negative x. I can't just add all the constant terms times e to the negative x's together, right? I have to add them so that their coefficients are the same also. If I were to multiply this all out, I could write a long factored form and do that, but that's more work than necessary, right? So if we simplify, I have my constant. I have 2 of these minus 4 of these, right? Minus 2 and minus 4. So they're all C7 coefficients. Here I have 2 and 1. Again, the coefficients match up also. So there's 3 of these. And then that leaves me with just this one, right? So it cleans up after each derivative pretty nicely. And then my fourth one, I have the product rule again for quite a bit, right? So here it's just 6. Here, this is going to be, this constant goes away. This one goes here. The negatives cancel, that's why it's positive. These two are the product rule of this one, right? So 3 times the derivative of the inside. E to the x stays the same. Here, same thing. The negative comes to the out, and the inside stays the same. And then this one, product rules to give us these two values also. Okay, so same thing. Differentiate the inside times the exponential. Here, the inside stays the same, and the exponential came out and gave us a positive, right? So again, here I have some similar terms. Okay, so I can add those together. And then I also have 2 more like terms here. So y to the fourth derivative, simplifies a lot more than the others actually. Okay, so now that I have the fourth, I can now substitute everything in, and the terrible thing here is I did all of this work, but I only need the second one and the fourth one because that's what my equation has. Right, so I just need these two. I basically need y to the fourth derivative minus y to the second derivative. And when I plug that in, I put my pieces, right? This is the fourth term, okay, here, right? And minus the second derivative. If I had space, I would say that this equals my g of x function, but I'm not going to write that right now. One, because I don't have space. I'd have to write it on the second line, and it'd probably be confusing. And also, I'm really just going to work on simplifying this down. Okay, I really just, now is where I combine like terms. I try to get things to just simplify to one single thing. Okay, and so I will distribute and add and all those good things, right? Remember that I'm subtracting this whole thing, right? So it might be nice for you to say minus and then put your yp in parentheses, but if you notice, I didn't, but when I did the math, I kept it into consideration. Okay, so I'm subtracting all of these things. So maybe if I go back, I'll actually write these in parentheses, right? But the answers are correct. Okay, so you just keep working things down. All right, so I have 12 minus 2 here, so that's why I have the 10. So again, I should have wrote parentheses, but I did do the math correctly, right? So as it's written, it does not look the same, but it is this thing minus this thing. I should distribute this negative everywhere. I did that in my head when I did the math though. Okay, so this is what we get down. Okay, so right away a lot of things cancel, right? Again, I'm trying to go over this slowly so you have time to write things down and kind of, you know, work through the problem. But for the C7 terms, I have the 12 minus the 2. So again, these are the ones with the e to the x, right? And then I have some more terms here when I multiply this out. And again, just do this on your own and make sure you get down to the same thing, okay? Because there's a lot of work once you multiply these out. You actually don't have to multiply it all out because there's a lot of similar terms, right? If you notice here, for the x terms, it's in a factored form, but I also have it showing up here in a factored form. I have minus 4 of them and minus 2 of them, but I'm minusing a minus, right? So what does that give me, right? That should give me end up with a negative 2 of those, right? Negative 4 basically plus 2 is still negative 2, right? So that's where this one comes from. The c7x squared plus c8x squared, I have a positive one here. I'm subtracting another positive one, though that completely goes away. That's why you don't see any c7x squares plus c8x's times e to the negative coefficient. We talked through this one, and these two right here are the only ones that show up, and they show up over here. So that's why you have the minus and the negative one also. Okay, so just to clarify, the math is right here. Ideally, it would have looked better to have parentheses around this term, but that's okay because I put the under brackets here. Okay, so it's this term minus this term. So now I can start to simplify this down, right? And that's what I did here. So all I did from this line to this line was distribute this negative 2, right? Once I got to that line, there's nothing that combines, right? I have c5x, a c6. I have two c7s, but they have different values of x. And then I have my e to the negative x term with no multiples, right? So this is as far as it goes. So this is the general form of my yp, my particular solution. And as you can see, that's what y to the fourth minus y double prime was. That's equal to g of x. So if this has to then be equal to g of x, right? Right. So again, this is my differential equation. It's equal to this, which I just simplified down, which is equal to this. So here I have the actual solution, and my solution also looks like this. So now I got to start making some equations and forming a system of equations. So I gotta equate each of the pieces, right? So I'm looking at the coefficients. So if you notice here, as far as the terms that have only an x, a coefficient times x, that's only this term, right? This has an e to the x, this has an e to the x, this has an e to the x. So that means that c5 times -6 has to equal 4, right? Here I have just a constant. There are no constants over here. That means c6 has to equal 0, okay? Here I have 10c7 equals e to the -x. Well, there is no just a constant times e to the negative x's, but there is a c7 over here that does show up in this form, right? So I really just have to set up a system of equations based on the coefficients that appear here, okay? So here we go. We're going to rewrite this, right? And we're going to set up our equations. So combining my like terms and setting the pieces equal to each other from one side of the equation to the other side, I have the following, right? So basically what I did was I took all the things that look like just e to the -x with no x term. I grouped them together and factored them out. That's really the most that I could do. So these coefficients are basically going to add up to 0 because I don't have a regular e to the -x on this side, right? I have e to the -x, but it's multiplied by an x here, like this, right? So all of these have to equal 0 because there's nothing over here. This also has to equal 0 and so forth, okay? So -6c5 equals 4, right? Because that's the coefficient here. That implies that c5 is -2/3, right? So I'm just solving this equation. Divide both sides by -6 and simplify your fractions. -2c6 equals 0 because there's no constants on this right side. Okay, so c6 is 0. -4c7, so I'm skipping this one and I'm jumping straight to this one because I can get an answer right away. This is the form that also shows up here. So those coefficients have to be the same, -4c7 and 2. So that gives me c7 is -1/2. c7 is here, and I know this has to equal 0. Right, 10c7 minus 2c8, it has to be 0 because that doesn't, there's no e to the -x over here by itself times a constant. So I can start to solve this, right? So I can plug in my c7 that I know is -1/2. So that gives me 10 to the -1/2 or -5. So I get -5 minus 2c8 is 0. So I will add 5 and then divide by -2. So c8 is -5/2. So now I have my coefficients that I can plug into here to get my general form. Okay, so these are my coefficients for this general form here. Sorry, not for this general form. We're going to plug those coefficients all the way into this general form. Okay, all the way back to the beginning because that was my solution. Right, what I have here is just the worked out form of y to the 4th derivative minus y double prime, right? So now that I have my coefficients, I will plug this into my general solution. So remember my general solution all the way back at the top that I just showed you looked like this. Okay, this was the general form. So we had that first part of the particular that we multiplied by x squared. And then we had that second part that we multiplied by x. That was the thing that we took the derivative of 4 times, right? So if I plug these coefficients back in to where they go, c5, c6, c7, and c8, this is going to be my particular solution. So now we have a general solution and our particular solution. So remember, a particular solution will not have any coefficients left, okay? So my full solution is that general solution I had, right, that we got from solving y to the 4th derivative minus y double prime minus now, or I would say added to yp. So yg plus yp, right, yg plus yp. Okay, so that is how we do solve by undetermined coefficients. Okay, so this is at about the 35-minute mark. Generally in class, I would give you guys a problem at this point, and that's what we would do for the remainder of class, and then I would go over it. I did not write a video up for it, and maybe I will, maybe I won't, but I think a better option is to give you the problem and have you submit it through Canvas, just like you're going to submit you submitted your homework today, and give you extra credit for it. Okay, so it'll be worth 5 points extra credit. Let me show you the problem right now. Okay, so I want you guys to solve this differential equation with these initial conditions. Write it on a piece of paper. Give me a full write-up. Don't skip any steps. I want to see the whole thing. Don't just write the solutions from the back of the book, because they don't show any work at all. There's absolutely no work on there at all. So if I don't see any work, I'm not going to give you guys any credit at all. We'll go ahead and upload that. I'll give you guys to the end of the day today, until midnight tonight, to submit this as extra credit. Okay. So I think that's pretty generous, because that gives you lots of time to sit down and work on it, instead of me saying it's done at 1 o'clock by the end of our regular class or what have you. So just hopefully you guys watch this video in a timely fashion so that you can go ahead and do that problem and submit that that write-up for me. Thanks to you guys for being patient. I'll send you guys out emails throughout the week, so make sure you guys are checking in. Okay, thank you.